Okay, so hello and welcome back. So now let's do a couple of examples using the circuit that we learned in the previous video. And basically, let's say that you have a lamp that needs a voltage of 28 volts, and it draws a current of basically 56 milliamp. And you want to use basically a transistor that whose beta is basically 100, and we want to basically feed this lamp using this transistor. So I draw the same circuit that we had in the previous video as let's say you have this resistor over here, and then it's connected to another resistor, and then it goes to ground. And then this point you connect it to the base of your transistor, and the emitter goes to ground. The collector is connected to the lamp, and the other end of the lamp goes to the positive supply ring. This is the V of S positive, and this is V of S negative. And then of course you need the switch, and this whole business of lamp and everything is because of this single pole single throw switch. And let's call this R1, for example. Let's call this R2, and let's say that basically your lamp is over here, and since I need 28 volt for this lamp, I set this voltage to the supply voltage to 28 volts. And I know that the beta of the transistor is 100, right? So basically this tells me that since basically 56 milliamp is required by this 56 milliamp of current is required by this lamp, the collector current of this transistor has to be 56 milliamps, which means that basically I can write I of C to I of B is equal to beta, which means that basically I of C is 56 into 10 raised to the power negative 3 amp to I of B is equal to 100, and that means that 100 times I of B is equal to 56 into 10 raised to the power negative 3 amp, which means that I of B is equal to 56 into 10 raised to the power negative 3 amp divided by 100, which is the same thing as 56 into 10 raised to the power negative 5 amp, right? So that means that your I of B is supposed to be 56 into 10 raised to the power negative 5 amps. Negative 5 amps. So that's basically your base current. And let me show you actually the currents over here on the circuit as well. So the current that comes in here is basically, let's call this I of 1, let's call this current I of 2, and let's call this current I of B, for example. So this current comes in here, and it's divided up to into two branches, I of B and I of 2. Which means that I of 1 is the same thing as I of 2 plus I of B, right? And that basically means that basically the value now in order to be able to calculate I of 1, I need to know the value of I of 2 over here, as you can see based on this equation. And we said that we would arbitrarily set I of 2 to 10 times, we would set I of 2 to 10 times I of B, right? So that means that I of 2 is the same thing as basically 10 times I of B would be 56 into 10 raised to the power negative 4 amps. So that means that I of 2 is the same thing as 56 into 10 raised to the power negative 4 amps. And basically I of 1 based on this would be equal to I of 2 plus I of b, which is equal to 56 into 10 raised to the power negative 4 amps plus I of b, which is 56 into 10 raised to the power negative 5 amps. Now you need to be careful here with this calculation because of the fact that basically adding these numbers is a little bit tricky, or at least I make mistakes here most of the time. So I can write this as 56 into 10 raised to the power negative 4 amp plus 56 into 10 raised to the power negative 4 into 10 raised to the power negative 1 amp, right? And that is the same thing as, and I can take 56 into 10 raised to the power negative 4 out, and that becomes 1 plus basically 10 raised to the power negative 1 all in amps. And that is basically 10 raised to the power negative 1, which is 0.1. So what? That's 1.1. That's 1.1 times, that's 56 into 10 raised to the power negative 4 times 1.1 all in amps. And that's the same thing as basically what is 56 times 11, and you have a decimal place in there, so 56 and 0, and then you have 56 there, so you have 6, 11, 1, 616, and that's 61.6. That is 61.6 into 10 raised to the power negative 4 in amps, which is the same thing as well, it doesn't matter what it is really. So it's important is that basically I of 1 is the same thing as 61.6 into 10 raised to the power negative 4 amps. So now that we know these currents, we can calculate the resistances. So to calculate these resistances, what we need to do is first of all, I know that basically I of 2 is that this is the value of I of 2 that goes through this resistor. If I apply the Ohm's law to this resistor, V is equal to IR. We know that basically the voltage across this resistor is the base emitter voltage of this transistor, which is 0.7 volts. The current. Okay, so basically we were applying the Ohm's law to this resistor R2, and we said that basically the voltage across the resistor is 0.7 volts, and basically the current going through that is 56 into 10 raised to the power negative 4 amp times R2, right? That means that R2 is the same thing as 0.7 volts divided by 56 into 10 raised to the power negative 4 amp, which is the same thing as now divide by 7, you will get a 0.1, divide by 7, you'll get an 8 over here. That's 8 times 7 is equal to 56, and then this is 10 raised to the power negative 1. So this becomes 10 raised to the power negative 3. 1/8 is the same thing as 0.125. So that's 0.125, sorry, 0.125 into 10 raised to the power 3 basically ohms, which is equal to 125 ohms. So that means that R2 is the same thing as 125 ohms. And then I can apply the same Ohm's law to the other resistor to calculate the value of the resistance here. So the voltage across this resistor is basically, you can imagine that it's basically the same thing as 28 volts, meaning that you can ignore basically the voltage drop across the resistor R2, which means that I can take this voltage as simply 28 volts, and the current going through this resistor I1 is 61.6 into 10 raised to the power negative 4 amp times R1, which means that R1 is the same thing as 28 volts divided by 61.6 into 10 raised to the power negative 4 amp. Give this to a calculator, you will get something like 28 divided by 61.6, that's 0.45. I take this as 0.45 into 10 raised to the power 4 ohm, which is the same thing as 4,500 ohm, which is the same thing as 4.5 kilo ohm, right? It means that R1 is equal to 4.5 kilo. And that's basically all of the values I1, I2, R1 and R2 related to this circuit. Okay? So as you can see, it's simple to basically to build circuits of using these transistors, and by now we know almost to do almost anything, at least using basically the bipolar junction transistor, of course, except for amplification, and that's I think the only thing that we will learn in this book at least is amplification. And then of course there is other types of transistors as well. There is the FET transistor, there is all types of FET transistors and all of those things, but we will go through them one by one. Now let's do another example here. This time let's say that, so let me check these values. I of B is equal to 56 milliamp, so that's 56 into 10 raised to the power negative 5 amp, which is the same thing as 56 milliamp. That is correct. And I of 2 is equal to 5.6 milliamp. 56 into 10 raised to the power negative 4. Negative 4 is the same thing as basically 5.6 milliamp, that's also correct. And R1 is equal to 4.5 kilo ohm, and R2 is equal to 125 ohms, right? So that's basically that. And the previous time that I tried to solve this circuit, and I got the value of for this resistor R1, I got the value of 450 ohms, which I mean didn't seem right to me. It's based on experience. You know that basically 450 ohm resistor would not work here using the whole situation, and you consider the whole situation, you know that 450 ohm, for example, would not be right in your circuit. And so I did the calculation again, and of course I checked my answer in the book, and I saw that basically I had made a mistake with one of the powers of 10 basically over here, right? Okay, so now let's say that basically we have another situation, and now basically this time we have a lamp that needs a 12 volts, that's a 12 volt lamp, 12 volt lamp that draws a current of 140 milliamp, and the beta of your transistor is 50, and you want to calculate the values of I1, I2, I of B, R1 and R2, right? Okay, so now let's say that you have this 12 volt lamp that draws a current of 140 milliamps. So I set my supply voltage to 12 volts, and since basically this lamp needs 140 milliamps, then I'm going to assume that then the collector current of this transistor I of C is basically 140 milliamps. So that means that I can say 140 milli into 10 raised to the power negative 3 amps is divided by I of B is the same thing as beta, which is equal to 50. That means that 50 times I of B is the same thing as 140 into 10 raised to the power negative 3 amp, which means that I of B is the same thing as 140 into 10 raised to the power negative 3 amp divided by 50 divided by 10, you'll get 5, divided by 10, you'll get 14. 14 fifths is the same thing as 2.8. That's 2.8 into 10 raised to the power negative 3 amps. That's 2.8 milliamps. So that means that I of B is equal to 2.8 milliamps. That's your base current, this current over here, right? And since now we know our base current, we can calculate I of 2 here. We take basically this, so essentially in this circuit we know that basically I of 1, we know that I of 1 is the same thing as I of 2 plus I of B, and I take I of 2 as basically 10 times, arbitrarily as 10 times I of B, and therefore I of 2 would be equal to basically 28 milliamps. So I of 2 would be equal to 28 milliamps, right? And therefore I of 1 would be equal to I of 2, which is equal to 28 milliamps, plus I of B, which is 2.8 milliamps. And that's the same thing as basically, let's say 2.8 into 10 raised into 10 plus 2.8, and this is in milliamps, and this is also in milliamps, and that's the same thing as basically 2.8. If I take out, I'll get basically 10 plus 1 in milliamps, which is the same thing as 2.8 into 11 milliamps, which is the same thing as 28 times 11, and at decimal point you have 28, 0, and you have 28 there, so you have 801, 308 is equal to 308 milliamps. So I of 1 is equal to 308 milliamps, which doesn't make much sense. I think I made a mistake over here. So this is 28 milliamps plus 2.8 milliamps, which is 30, not 300. So this is 2.8 into 10, which is 28 milliamps plus 2.8 milliamps. And then take the 2.8 out, we'll get 2.8 times 10 plus 1, which is equal to 11. 11 times 2.8. That's 30.8, I'm sorry, 30.8 milliamps. 30.8 milliamps. Okay, so now we have all of these currents over here. And since we have the currents required, we can calculate the value of these resistors. The value of R2, for example, if I apply the Ohm's law to this resistor, is basically the voltage across this resistor, which is 0.7 volts, is the current through that, which is 28 milliamps, 28 into 10 raised to the power negative 3 amps, times R2. which is basically R2 is equal to 0.7 volts divided by 28 into 10 raised to the power negative 3 amps. Now divide this by 7 times 4 is equal to 28, so that's 0.1, and that's a 4, and this is 10 raised to the power negative 1, so you can write this as 10 raised to the power negative 2, and 1/4 is the same thing as 0.25 into 10 raised to the power 2 ohm, which is equal to 25 ohm, right? That's 25 ohm. R2 is supposed to be 25 ohm. And basically applying Ohm's law to resistor R1 over here, so we can say that basically the voltage across this R1, you can take it as the whole voltage because you can ignore the voltage drop across R2. So I can say that 12 volts is basically the current through R1, which is I1, which is 30.8 into 10 raised to the power negative 3 amps times R1, and therefore R1 is equal to 12 volts divided by 30.8 into 10 raised to the power negative 3 amps. And what is that? We can calculate it on the calculator. 12 divided by 30.8 is 0.39, let's say. 0.39 into 10 raised to the power 3 into 10 raised to the power 3 ohm, which is equal to 390 ohm. So that means that R1 is equal to 390 ohm. So hopefully the 400 ohm and 25 ohm, the values are correct without any problems, and we can build this circuit this way as well, right? Okay. Now I'm going to do, well, probably one more example here before jumping to AC circuits. So I'm going to pick one of the examples here. Probably two of them or one of them or something like that. So I'll see you in the next video with a couple more of these examples. Thank you.